All right, students, welcome to your second day of lecture. Today we'll be tackling the next two types of bondings. There's a total of three main types of bondings that we address in chemistry. We went through ionic bonding yesterday, and you guys learned about polyatomics, a unique set of grouped atoms that together carry a charge. You learned about how we pair a metal plus a non-metal, or a cation plus an anion, right? And you're responsible for memorizing polyatomic names and their charges, and of course, how we can tell when to bond atoms together via both electronegativity principles, most paired with least electronegative on the periodic table, as well as your charges of the cation and anion when added together must cancel out to zero, right? And so now we're going to move on to our second type of bonding, known as covalent. So just like yesterday, I want you guys to look at these three covalent molecules, the three examples of covalently bonded compounds, and tell me what you notice, and pause me when you're ready, and then we'll resume. Okay, so hopefully you pause me for a little bit. And what we have here is one thing that you should notice is we are mainly working with non-metals. Like these happen to be mainly non-metals. So it's a non-metal plus a non-metal bonding is what we're seeing, okay? We're also seeing some similarity in terms of naming rules. We do have IDE sticking with us. So we have adding IDE at end of second, okay, element in bond. You also should have noticed that we still have the principle of the slightly more positive or less electronegative atom goes first. So the less electro, and I'm actually just going to write E/N because that's faster. The less electronegative atom, the more positive. But notice this is not a cation anymore. This is not a full charge. We're not seeing any full charge canceling here. So something else is happening. The less electronegative atom goes first. Okay. And the more electronegative atom goes second. Okay, the more negative. But again, we don't have a full charge here. We're not seeing a full anion being paired with a full cation. We're just seeing, okay, there's a small difference, okay? That's kind of similar to what we learned in ionic bonding. You also should notice something really interesting is that in the name, you're seeing what we call these Greek prefixes. You're almost seeing us tell you the amount of atoms in the molecule, which we didn't do with ionic. So you see the use of Greek prefixes, and it tells us directly the number of atoms involved. All right. So that's some of the patterns that you might have seen. All right. And so let's get into the characteristics of covalent bonding. So covalent bonding is a method of bonding where two or more atoms, share electrons. No full charge obtained or carried. So remember how we said that the goal is that all atoms want access to 8 valence electrons? And I said that word access would become a very important word because what it tells us is we don't necessarily have to own, because when you own electrons all to yourself, that's when you carry a charge. But if you want access, what you're really saying is you just want to be able to get your hands on it. So you really just need the ability to share and make sure through your sharing that you can get 8. Okay. So as far as the role of electronegativity goes, the same principle is that electronegativity of atoms in covalent bonds determines, okay, how the electrons are shared. So like in ionic bonding, it determined, okay, for us, how the electrons were transferred. But here it's determining, well, we're not doing a full transfer. It's not about determining who gets them and who doesn't. Now it's all about determining via electronegativity patterns who shares them a little bit better than the other ones, who gets a little bit more access to them than maybe another one, but they're technically still shared, right? So it's all about how you share. What we say is equally or unequally. Kind of like when you think about when your mom asks you to share something with your sibling. Yeah, you're technically sharing, right? You're still sharing, but sometimes you share a little bit worse than what your mom imagined, right? So let's look at some examples of covalent molecules that we've already seen. The first is diatomic molecules, and diatomic molecules are those atoms or those are those elements that cannot actually handle being alone, so they create a molecule with themselves. So we said bromine can't actually handle being alone. It'll create a molecule of Br2, which is, by the way, Br bonded with Br. Okay. Um, Iodine, also, when you think it's alone, it's actually partnered together. You'll never see a single iodine atom in space. It'll always be paired with another iodine. Nitrogen, chlorine, hydrogen, oxygen, and fluorine are all examples of diatomic molecules or covalently bonded molecules where they're sharing electrons. I like to call it Dr. Brinkelhoff diatomic molecules, Brinclhof, Brinkelhoff, as a memorization tool, because you do want to know about these atoms. These molecules. You do want to memorize these diatomic molecules. We also have actually already talked about molecular, okay, or covalently bonded molecules by actually looking at polyatomics when they're alone and not in an ionic bond. Remember how we said they're a group of bonded atoms that together carry a charge? Well, as long as that group of as long as a group of covalently bonded atoms are not actually in a bond when they're standalone, they're an example of a covalent molecule. So for example, PO4 3 minus alone is covalent. Okay. As long as we don't put it in with another ion, if it's just free floating alone, it's actually an example of a covalent molecule where between the phosphorus and the 4 oxygens, they are sharing. We see sharing of electrons. Okay. So, covalently bonded molecules or molecular bonding is really unique because since they're sharing, there's a lot more possibility. It's not so one-to-one, like you give, I take, that's it. Now we can share less or more. So what we can say is we have a single bond where 2 electrons are shared. We can have a double bond where 4 electrons are shared between atoms. And we can have a triple bond where 6 electrons are shared between atoms. These double and triple bonds are also called multiple bonds as a general category because you're creating more than one. So if I said, oh, I formed a multiple bond, that could be telling you I formed a double or a triple, anything greater than 1 bond, anything greater than 2 shared electrons. So as a little summary table, what we'd say for single is that if you had atoms, okay, atom X and atom A sharing, we'd say that there were 2 electrons being shared, okay? For double bonds, we'd say that there are 4 electrons being shared. And for triple bonds, there are 6 electrons being shared. Now, we often draw it as just 1 line, 2 lines, or 3 lines for a shorthand when we reference and illustrate bonding patterns between covalent sharing electron compounds, okay, or molecules. And there's an actual relative strength that we pair with this. Single bonds, we say, are the lowest in types of bonding strength. Doubles are the middle. And triple are the strongest. Okay, it's kind of like holding on to one person with 1 finger versus 2 fingers versus like a full hand grip, right? It just gets stronger the more you share, the more interconnected you are. Okay. So when we name covalent molecules, we have some pretty similar rules. We always put the less electronegative, the more positive atom first, and then we put the more electronegative, atoms second, and we change it to IDE. That's pretty standard. Instead of having full-on charges, we're just now saying more versus less. Okay, but what is unique is that now we tell the listener, now we tell exactly how many atoms are involved using Greek prefixes. Okay, so because we don't have charges to just mathematically figure out how many we need, now we just have to tell you because there's no way you would know. So our Greek prefixes are very geometrically connected. Mono means one, di, two, tri, triangle, three, tetra, four, penta, five, hexa, six, hepta, seven, octa, eight, nona, nine, deca, 10. All right. And so what you see is a series of examples. And so one thing that you'll notice is that we never use Greek prefixes mono. We don't write for the first element, but we will write mono for the second element. Okay, monoxide, a one oxygen, okay, compound. But we wouldn't say monocarbon because we assume, at least when starting off the name, if you mentioned the atom in the first place, there's got to be at least one. Okay, it's a slightly unique rule to keep in mind, but otherwise we just use it as standard. We just put it in front. It's a prefix, so it goes in front of the element, and we just tell the reader how many of those elements we have. So for example, what's the formula for nitrogen dioxide? Well, nitrogen and two oxygens. What's the formula for xenon tetrachloride? Xenon and four chlorines in a bond, chlorides. Now pause. If you're like, excuse me, I thought xenons are noble gases and they're not reactive. Okay, so here's a little special thing to know. There are certain circumstances known as expanded octet moments when your molecule requires one atom to carry more than 8. Okay, and so what we're going to see is that sometimes noble gases are selectively reactive when your molecule requires more than 8 electron access. But I'm just going to leave it at that and say more on this later because I'm going to teach you this in a couple days. How to know and why that works. Why we seem to be breaking the octet rule. Okay? But just so you know, it technically is possible. Why am I having such a hard time writing this word? It technically is possible to have a noble gas be in a reaction. Okay? It just has to be very specific circumstances. Okay? And then of course we have the last one. What's the formula for dinitrogen? Nitrogen 2, pentoxide, oxygen 5. And notice we're still using the small number subscripts to represent the amount of atoms bonded together in a molecule. So go ahead and try the next 2 examples on your own and just pause me for like 1 minute. Okay, so hopefully you have it and you should have gotten sulfur hexafluoride and carbon tetrachloride. Okay. So couple notes about covalent compounds when they form solid structures. Okay. What we have is 2 types of structures that can come through covalent molecules or sharing electron molecules. The first one is known as a network covalent solid, and it's basically one giant molecule, kind of like with a ionic compound lattice structure. It's basically everybody sharing electrons. Like you share electrons across the whole molecule, the whole like solid, basically. You share electrons across the whole solid. So it just becomes one giant molecule. Oof, that got really bad. One giant molecule across the whole solid. But then there's a second type known as a molecular solid, where these solid molecules have individual molecules connected through intermolecular molecular forces. But notice, this is not sharing across molecule. We're not sharing electrons across the molecule here. Or across the whole solid, to put it in comparison terms. So this is a slightly different way. You can kind of think of the other one, network covalent solids, is like the Monsters Inc., like the blob, like everything just kind of merges into one giant thing. Whereas molecular solids is like something holding hands with something else. That you can still separate the individual parts, but they kind of just hold hands together and group up to make something similar. Okay. So I want you guys, before we move on to the rest of lecture and the third type of bonding, I want you guys just to take 5 to 10 minutes to walk through a couple workbook problems in your Unit 3 workbook that, again, you can download on Canvas or my website, and go through about 5 to 6 examples, all right, with your TAs. And try them alone, and then your TAs will walk over the answers with you. And of course, if anyone's stuck, you can always Google it too. But try doing without Google, and then resume this video when you're ready. Okay, so hopefully you only spent about 5 minutes, 5 to 10 minutes looking at some workbook problems. And let's go ahead and move on to the type number 3. And this is the easiest type of bonding to understand, because metallic bonds are formed between metals and only metals. And what happens here is, what we say is that the metal atoms create a shared pool of electrons. And we call this shared pool of electrons a sea of electrons. Remember, metals want to lose their electrons, but let's say a metal can't find an anion. What it'll do is it'll just kind of go with its platonic group of metal friends and just pool all of their electrons and become both give and receive accordingly. So it doesn't really, no one's fully gaining any electrons. And even though no one's fully losing any electrons, it kind of creates a pseudo effect. All right. Kind of like when you go to a homecoming or a dance with a group of friends, like no one's actually out on a date. You're just kind of all hanging out and you're all, making it somewhat enjoyable, and you're getting what you need, right? You're getting, one, enough money to go out for dinner, and two, a group to hang out with. Okay. And so what we see is there are 3 types of structures between how the metals can mix and share. The first is, if you're using the same metal and you're creating a bond between the same type of metal, it just gets what we call a pure metal. But let's say you have an alloy. An alloy is a metal mixture. So like steel. Steel is an alloy, okay? A mixture of different metallic atoms that are together pooling their electrons, and they're around the same size. We call those substitutional alloys structurally. And then let's say you have a couple metals alloys with different size, like where one metal atom is definitely bigger than the other metal atom. We call those interstitial alloy structures, because the metal atoms, even though they're all sharing electrons, the smaller metal atom will fit between the crevices of the larger metal atoms. Idea, though, is they all share electrons in the sea of electrons. Okay. And so as a result, by the way, this explains why metals have certain properties. Why are metals able to be so dense? It's because we can squish the sea of electrons. It's very fluid. Okay. Why are metals able to be shaped? Same reason. You can squish the sea of electrons, and so that you can create more compact atom to atom interaction. But you also see why it has conductivity. A sea of electrons, it means that electrical currents flow through the sea. Okay. And electrical currents are electrons being shot through. So if you have a sea of electrons and you just shoot more through, they'll just maneuver themselves really quickly through the metal. All right. So that's the end of that. It's a much shorter day today because I wanted to give you guys ample time to do a couple things. First and foremost, okay, you should do some workbook problems. Like, you need to study for your quiz tomorrow on naming rules. You need to memorize your polyatomics. You need to memorize the different rules between ionic naming compounds and covalent molecule naming using Greek prefixes now. Okay. Metal naming is easy. It's just the metal. Okay. You also should make sure that you're up to date on Canvas. And I did release a extra credit assignment where you can make this up an illustrative story to show me through creative means how things bond. All right. And so all the details of that are on Canvas. And I believe there might be even one more thing oh, you should have some lab station practice. There's some station practice printed that my TAs can set up at each station where you can practice naming as well as some of the older stuff too, so you don't lose it. Electron configuration, reminding yourself of the periodic table patterns that help us understand some of this reactivity stuff, right? Especially with the role of electronegativity and predicting for ionic compounds, which metals will bond, and for covalent compounds, how electrons share, right? And so you have plenty of time, plenty of work. No one should be goofing off. And I look forward to being back tomorrow. Thank you to the sub who's watching over my class. I should have said that at the beginning. And if any of you are curious why there are so many seniors gone today, it's because there was a senior meeting during second period. So if you have a senior friend, by the way, please remind them. I should have sent them also an email via Canvas, but please remind them that they are expected to be ready for the quiz tomorrow, which means they should watch this video lecture on my website or through my agenda. All right, guys, really good luck. Email me if you have any particular questions, although I think you all should be fine to hold off until I get back. So see you all. Bye.